Hi everyone, I'm Francesco Penta and I'm a cloud support engineer at AWS and I'm based out of Dublin, Ireland. Welcome to AWS Supports You, where AWS support experts provide tips to optimize performance in the cloud, lower cost, and provide you with the best practices and design considerations. Joining me today is Milan Karalic from AWS Support. Can you give us a quick introduction, Milan?
Hi, everybody. My name is Milan. I'm a principal support engineer based in Dallas, Texas, and I'm very excited to be here today with you.
Thank you, Milan. So today we will be talking about evaluating networking performance, and we will focus specifically on the EC2 performance. But before we get into the details, a quick note to the attendees online. Feel free to use the chat window on the right-hand side of your screen to let us know where you're joining us from today and share your thoughts and questions throughout the episode. We look forward to hearing from you. We'll also provide a link to our survey, so if you'd like to let us know how we did, please click the link and leave your feedback. With that said, Milan, can you walk us through what we're going to be talking about today?
Awesome. Thank you, Francesco. So today we'll be talking about why networks matter and how does the picking up the right configuration fit into the your model of designing application. What are different network performance features that are present in AWS? Looking into the Nitro platform and then Elastic Network Adapter, and then looking again into the overall architectural performance and being aware of what are certain bandwidth limitations and how to design and how to scale them. And lastly, we're going to be touching about the important performance concepts and how to do performance testing.
Thank you, Milan. So, before we start diving into this, I just wanted to give a bit of context into why we decided to talk about this topic today. As you may know, customers use AWS for a lot of different purposes, from financial services to medical applications or their data storage, or simply to expand their data center on the cloud. So there's a lot of different architectures that our customers are building on top of AWS, but they all have one thing in common, and it's the use of the network. Me and Milan have been working here at AWS primarily on networking services, and we helped our customers build and troubleshoot a lot of their application and try to solve problems at any time they encounter one, and try to have them make the best decision regarding their networking design. But I noticed one thing when talking with customers about this, which is that not everyone is a network engineer. Not everyone is aware of what building a network means and what are some of the concepts that we're going to talk about. So some of the things that might seem evident to someone that doubles and works with networks might not be evident for everyone. So one of the questions I get a lot from our customers is the network a problem? And these are often happens every time something might go wrong with an application or with the expectation is always try to blame the network from the beginning. They will ask, oh, is going to be a problem? Or simply, even if there is no incident management mode or trying to figure out if improving the network is going to improve the performance of their applications. So there might be a few difficulties for customer trying to make the best decision here and try to select the best architecture. And it might just be tempting to throw the biggest systems type and the biggest and the service and resources at the problem. It's definitely the easiest way out, and definitely gives you all you need, but it's not necessarily cost efficient. So we are here today to talk a bit about the experience that we gained dealing with our customers and explaining what are the networking performance that they can expect, what are the limitations that are in place, and how to evaluate the performance that you have with your resources that you might need with your application. So I want to share those learnings with you today, and I'm going to pass a few links in the chat. Regarding the how you can learn a bit more with AWS networking with some of the immersion day workshops or the learning plan for advanced networking, as well as some of the customer success stories regarding network and content delivery, where you can learn what our customers are building on top of AWS. With that said, before we dive into the meat of the thing, I wanted to mention a few things regarding the network performance features. So how AWS allows you to get the maximum out of the network and what kind of expectations are in place. So Milan, do you want to talk a bit about the network performance features available to our customers?
Thank you, Francesco. So one of the key, things that we want to talk about today when it comes to the network performance is the, advancements in the EC2 Nitro space, where it's the custom platform that's purposely built hardware and software to work very closely together to maximize the available performance for our customers. It was launched in November 2017 with the introduction of C5 instances, and it's been in development since 2013. On top of the custom hardware and the software, there's also a custom hypervisor, which was developed specifically for the AWS within AWS. And every instance launch since has been using a Nitro hypervisor. So the Nitro system as a whole comprises of multiple things. So there are different Nitro cards, which enable access to the NVMe storage or EBS storage, as well as the networking, which is going to be primary focus of our talk today. There is a Nitro security chip, which is integrated component on the every motherboard of the hardware, and it protects the hardware resources. It also enables us to offer our customers bare metal instances, which are exactly that, your Intel, AMD, or Graviton platform as a whole without any hypervisor to run on top. So it's a real bare metal experience. And ultimately, the last component is the lightweight hypervisor that does the memory and CPU allocation and also provides a bare metal-like performance. So it's a very, very low level overhead hypervisor. When we zoom specifically into today's talk, and that's the networking benefits, and when we reflect the benefits of the Nitro system, we can see that with the introduction of the Nitro enhanced networking, we have been able to drive the significant increases in packets per second that are available to the instances when comparing to non-Nitro instance types. We have been able to increase reduce the latency between instance to instance communication with the implementing technologies such as single root I/O virtualization with the PCIe pass-throughs, bypassing the hypervisor completely out of the way, and you're providing a very consistent performance. Enhanced networking in AWS comes in two flavors, which is the Intel IXGBVF, which is the old Intel-based enhanced networking available in C3 instance families, and then ENA, which stands for Amazon Elastic Compute Classic Network Adapter. So when we zoom in into like the full overview of the architecture of a Nitro system, we can see that there are multiple Nitro cards on the PCI bus, and they all have different components that provide, either storage offload, networking offload, or the instant storage access, or sorry, the EBS access as well. Over the time, when we look at the different generations of the instance families, we can see the significant increases in available throughput to an instance, especially like we go all the way back. The original instance family M1 had a maximum bandwidth of 1 gigabit per second, which at the time was a lot. But our customers' appetite has grown and their environments became more complex. So we were innovating in order to keep up pace with the rapid changes in the customer requirements. So the first instance type which introduced enhanced networking was C3, and it provided up to 10 gigabits per second. So it was a 10x increase. But recently we have announced P4DN, which is one of our latest instances for machine learning, and it can drive up to 400 gigabits per second. And it's not where we're stopping. There are some other instances which are in preview mode, such as TRN1, which can drive even higher, 800 gigabits per second. And now, so we've talked about what are the important things. I want to give it to Francesco to talk a little bit more about why is it important to pick the right architecture.
Thank you, Milan. So before we go into that, we have a question from Rella Kaje. So the first question is, what exactly does AWS mean by network performance? So network performance is something that is a generic term that is used across evaluating network quality of service. There's no specific way to benchmark this because it will depend, and we'll see that in a few minutes, really on what you are expecting. But mostly we're talking about bandwidth, latency, throughput, number of packets per second that you can send. So basically measuring quantitatively the expectation that you can get so that your application can run smoothly. We'll have a section dedicated to this, so stay with us and we'll cover this in a bit more detail. And thank you very much for your question. Now, before we go into that, just wanted to touch on the architectural performance, because when we're having this level of discussion in terms of what should I use and what are the limitations that are in place, a lot of customers approach these with a traditional mindset. So one that might have with their on-premise data center, where they have to provision and build their infrastructure, selecting switches and routers, and even simply selection of network cables and subscribers, which will have limitation in them by themselves. So the first thing that we have to have this conversation with our customers that the source and destination matter when you are evaluating network performance. And this means that if you're running instances close in a single placement group, or if your source and destinations are over a VPN connection or a direct connect, or you're using a load balancer to distribute traffic across your instances, or even using other services that are not directly related to EC2. We will focus on EC2 for this presentation, but we'll give a few indications of what your expectation when accessing services like S3 or even remote services over the internet. Again, as customers are coming with a more traditional mindset, they will often ask us what are the limits of their VPC. And for those that might not be aware of the concept, VPC stands for Virtual Private Cloud, and it is a construct that you can use in AWS to define your own virtual private cloud. Think about it as like your data center network. VPC is a software-defined network, which means that you don't have switches and routers that are supporting it. So you do not have this level of limitation and bandwidth capabilities that you normally have in a traditional network. Obviously, there is some hardware supporting it, but it's abstracted and run by AWS in order to give you high performance and basically endless scalability. For the same reason, we are talking about no limits when you're talking about availability zones or subnets. There's no limits when you are going through the internet through an internet gateway, and for the same reason as well with a VPC peering within a region, since VPCs are again software defined and a virtual construct, you're still able to achieve a maximum performance. So we'll see a bit more what is that define those limits, which is surprise, surprise, a bit of a spoiler, EC2. But again, it is something that we'll touch in a bit more details. So the only consideration here is that the NAT gateway do have some limitation on the maximum bandwidth it supports, but it starts with 5 gigabit per second and grows all the way up to 45 gigabit per second. You can always scale by adding more NAT gateway per subnet and dividing your traffic. But again, when you have those kind of use cases, that should be plenty of bandwidth, and you might not be using the right architecture at this given moment. So going back to the customers that use more traditional approaches or that are still using the cloud in a hybrid manner approach with their connection data center, there's two main ways of connecting to your on-premise network, which is mostly, so there are other ways, but those are the two main ones our customers use. And the first one would be through site-to-site VPN. In that case, we do have limitation here, which is 1.25 gigabit per second per VPN tunnel. You can work around this limitation when using transit gateway, using equal cost multipathing, so aggregating multiple, so distributing traffic across multiple tunnels and achieving more than this. We do have some customers that are using these heavily in terms of capabilities using ECMP. And for direct connect, you are only limited by the physical port speed. So you have 1, 10, and 100 gigabit. Same thing, you can do ECMP across multiple links if you need. So, there's plenty of options there as well. Um, uh, that's more or less it. Before we go to the next section, Milan, we have another question from Monramon357. What are the VPC endpoints that are available? So the VPC endpoints are available for a lot of different services. I'll post a link with the list, so otherwise it will take a bit of time. You do have the ability of having your own custom endpoints as well, but look forward to the link. I'll go grab that for you in a second, and you'll have the list in there. So Milan, back to you to talk a bit about performance concepts.
Awesome. Thank you, Francesca, and thank you, Manuel, for your question. While we wait for the link, I wanted to touch base on what are the basic performance concepts that we need to understand, so we can be better equipped in understanding overall network performance, but also when we're troubleshooting things. So on this topic, obvious one is the bandwidth, which is what is the maximum size of the link that your physical link supports, be it or in an EC2 world, what is the maximum bandwidth that's available to an instance. And that can be like 10 gigabits per second, 25, 100, 400. Latency is another term that we need to understand. And that just represents what is the time that it takes for a given packet to reach the destination in one case, and then to come back to this source, to the sender. And this trip measured in latency represents the round trip time of a packet, which is how long does it take to go there and how long does it take to get the acknowledgement back from the sender. A throughput is a derived thing, and it's basically what is the current bandwidth that my instance or my application is driving. And it sometimes can be equal to the bandwidth, which is basically you're achieving the maximum throughput for the given bandwidth, but it's heavily impacted by latency as well as the potential packet loss along the line and jitter, which is something that we're not going to be spending a lot of time talking about, but it's important to remember for those folks who are deploying real-time systems or like any type of voice over IP or video streaming. Jitter as a concept represents nothing else than a rate of the packets which are being reordered in a given like time interval. So whenever the jitter happens on a steady link, where you always have the packets arriving in the same pace, when there is a packet which is a little bit out of the order, you can get the modulation on the stream, or like your video might skip or reduce the quality of the stream at that given point in time. And in a scenario that we want to understand, like in this hypothetical scenario, what is the maximum bandwidth that we can get from between two of the EC2 instances? And let's say that we have a bandwidth of 10 gigabits per second, and that our single distance latency is 500 milliseconds. So it takes us 500 milliseconds to send this packet. If we were to send it, it's going to generate an acknowledgement from the receiver, and that acknowledgement is also going to have to travel for 500 milliseconds, so giving us a total round trip time of a single second. Obviously, this is very napkin math and simplified for the sake of understanding, but we can say that in a given second we were able to transfer a single packet, and our bandwidth represents how many packets were we able to transfer per second and what was the size of each packet. So if this packet was 1 kilobyte size, our bandwidth would be 1 kilobyte per second in this particular scenario. So what can we do to increase the bandwidth? Well, obviously we can send more packets, and this is what happens in reality. There's it's not always a single packet, but we send more packets, and that way we are having them in flight in parallel, so we're not serializing them and waiting for them sequentially to arrive. The way we can further increase it is changing the size of the packet, because we know that the latency is not going to change, but what we can affect is what is the size of the data that we're transmitting. And in networks, it's directed by the maximum transmission unit, which is a property of the IP protocol, and it tells us nothing else than what is the maximum size of the packet that you can send before it gets fragmented, or depending on the configuration of the devices, it might get dropped, or some other things that you have to take care of in the use cases. But also, like when we talk about more packets, one of the things that we can do is we can tweak the protocol itself. In this case, we'll be talking about TCP, and we can say, hey, we can send more packets. Rather than sending a packet at a time, we can say we can send more packets, and this is often referred to TCP window size. And this is something that dynamically gets adjusted over the period of a connection, and we'll see a little bit later about that. But it's important to remember that in this equation there's a thing that at this point in time we cannot change, which is simply the round trip time. Obviously, we can optimize it by bringing these things together closer, and we'll see a little bit about what are our options in that front. So TCP and latency is like latency, as I said, is a major factor for a lot of things, especially when we talk about things like cross-region connectivity. It takes time for a packet simply to go from point A to point B, and the further they are away, the latency is higher. So we have to take care of those use cases for us. But also, it's very important when we talk about high performance computing and the placement of the different instances. How close are they to each other? Because when you have a very highly distributed cluster that's processing a lot of data, if there is a latency in between the nodes, there is an idle capacity that's not doing the unit of work which it could have done if it got all the required packets from the network to continue working. It's also important, like in technologies such as Amazon Elasticache or Memcache, where we often add these to increase the performance of our application to reduce the latency of, let's say, lookups for the relational databases. So it's very important that these systems are performing in a very low latency manner, so they give a response back faster, so the content gets served to our customers faster. So what are our options when we're dealing with it? As I mentioned earlier, we can increase the maximum transmission unit. We can send more packets. However, there is a little bit of that's out of our control, which is the default maximum transmission unit size across the internet, which is usually 1500 bytes. So when you're within your data center or your VPC, you can tune it and you can change it. But the moment the packet egresses towards the internet, its maximum transmission size is going to be 1500. And then there are some ways where you can increase the throughput by employing the private links and whatnot, but it's outside of the scope for now. Other thing that we can talk about is TCP tuning. What are the things that we can change on our protocol level that can influence how the protocol behaves? Like maybe it's a faster retransmission, maybe it's the increased window size that's available for a TCP connection. And we'll see a little bit more about that later. The third thing we can do is just increase the overall network efficiency. If we are being consistently present at a certain high bandwidth, and we are maxing out our link, well, maybe it's the time to get a bigger instance, or rethink about scaling. How can we deploy our application so we break down the available bandwidth requirements, but also increase our availability, overall availability of the system, because we have multiple components now. And lastly, when we talk about latency, is just making friends with physics, and that's one of the things that we have not solved yet, but one day it will be solved probably. And it's understanding where you deploy your applications. AWS region choice is very important, obviously from regulatory requirements, but also the distance to your end users. Usually these are in tens of milliseconds in latency. There are ways that employing technology such as CloudFront, Global WAN, Cloud WAN, sorry, you can bring a global accelerator. You can reduce the latency for the end users, but ultimately, these are very specific for certain use cases. When we zoom in within the region, the latency drops significantly to milliseconds. But it's very important to remember that there are certain workloads such as high performance clustering which require very very low latency, and that's where we talk about placement groups, specifically cluster placement groups, where we put nodes very close together so they are able to drive sub millisecond latency for these workloads.
Thank you,
And
Milan. So we have one question from Relacage, and is does excessive latency affect the throughput? And there's no simple answer here, but I will say that latency does affect throughput. And this is at least for TCP, as you have to wait for an acknowledgement for the data that you sent, as Milan was explaining before with during the bandwidth delay product. The amount of data that you can transmit is how much data you can send on the wire in that round trip time. And again, MTU, you're limited by that. You can send more packets, but when you're sending more packets, it increases the probability that a packet will be lost across the network, especially if you have a high latency. That means that there's likely a lot of hops and devices in the path from you to the destination, which again can increase likeliness of a packet being dropped. And the TCP, and we'll see that in a bit more details, uses congestion control algorithms to figure out how much should send on the wire. And again, latency not directly might affect that. So you can use a bandwidth delay calculator online to figure out what is the maximum theoretical bandwidth throughput that you can achieve, and then play a bit with the expected packet loss and whatnot. But we will touch about all of these in a few minutes. And again, thank you very much for the question. To add to what Milan was saying is it's very important how you building things out. You want to give the best experience possible. Sometimes it's not only about the bandwidth of the throughput itself, but also in how a transaction gets executed. So let's say that you have a chat service or something that allows customers to interact freely over the internet. If there's a lot of latency, people that have a half a second or 1 second or even simply a game service might get a very bad experience simply because every time they're taking an action, they have to wait for that second for the outcome of that action, either be a chat or if they're playing a game. So that's why it's important to place your service as close as possible to your customers. And if that's not possible, use things like Global Accelerator or CDNs so that you can shorten the distance in between customer and your service. So going there, and I like that we're getting a lot of those questions where the answer is it depends. And the reason why is there's a lot of benefits into testing performance. This is not something that we just tell people so that we can have them go away, but because there's a lot of different variables into figuring out what are both the expectations and both the capabilities of the network that you're using in the EC2 instances. Because besides selecting the right instance type, which might certain capabilities, you need to think a bit about your application. If you're using TCP versus UDP, how much data you're sending. Again, it is a transactional service where latency is very important, or are you transferring a lot of data where latency is less of a factor? But also your application plays a big role in how you're going to use the network. Because beside these, your application needs to do something with those packets. If the packets are arriving out of order, then it needs to wait for all the packets to arrive. You need to figure out what is the protocol you need to use, but also how you're consuming that. So is your CPU, memory, or even the disk going to be a limiting factor? We do see these a lot with customers sometimes when they are uploading data where they think that the network is slow, and simply because they are not able to achieve the advertised throughput. And when investigating, we end up figuring out that maybe they haven't selected the right type of disk, so they are limited by either IO or simply throughput from the instance to the disk. So the application itself, the operating system is telling the sender to slow down because it cannot keep up with the data being sent. So for this reason, we are telling always people to test themselves. Anytime they're building something, either test from the atomic unit, so the EC2 instance or the service or the application they're using, all the way to their entire application. And I posted a link on how to do benchmarking. So we'll cover some of these concepts later, but you have a step-by-step guide on how to evaluate these on your own. The first thing that normally I will recommend customers is to have an idea of what they want to achieve, and figuring out based on the expected user count or expected user profile, what is they're going to consume. From there, then they can go and try to figure out what is the best instance they can find, and either as a single instance or a group of instances they're going to scale. You can find the bandwidth characteristic of the instances on the documentation, but also in the console and using the CLI. One important thing and consideration to make here is that we do advertise the baseline of the instance and the burst capabilities. Burst capabilities are up to means simply that that instance will be able to reach that level of performance, but only for limited periods of time. And this is in order to give you the best experience possible if you're receiving a peak in traffic, or do you need for a small amount of time higher than usual performances, again, following a peak or a specific operation that is might be a bit more resource intensive. So keep that in mind when evaluating this. Next slide, we can see how we can use the CLI to filter the network capabilities of the instance by instance type. As you can see from the filter itself, we are describing all the instance types in the C5N family, and then using the query to filter it by the network performances. So that will provide a table that has all you need, and this might be quite useful if you are doing automatic testing, or if you want to integrate this in your day-to-day automation rather than having a reference the documentation every time. And that will always have the up-to-date information about the instance types and what their capabilities are. Last couple of considerations to make is that, as we saw in the VPC page and the slide, we don't really have bandwidth limitation, but there are limitations when you're sending data from and to an instance. So as long as you're staying in the same region, you're able to achieve the full bandwidth in between two instances as advertised. But if you're moving to another regions, or you're going through the internet gateway to the internet, or using direct connect, if you have fewer than 32 virtual CPUs on the instance, you will be limited to a total of 5 gigabits per second. While if you have more than 32 virtual CPUs, you have 50% of the network bandwidth available to that instance type, which means that if the instance is 25 gigabits per second as a limit, and more than 32, and you're going out of the region, then you will be limited to 12.5 gigabyte. The important consideration to make here, though, is that this is the maximum amount of bandwidth the distance can achieve. You are still limited to 5 gigabit per second per single flow. And by single flow, we mean five tuple where you have the protocol source and port and IP and the destination port and IP that will indicate the single flow, and that will still be limited to 5 gigabit per second. This is not too much of an issue for most customers since you will have a number of clients or other part of the application using a number of different flows, which will allow you to grow beyond the 5 gigabit. But maybe for some customers, a bit of a limitation when you have a single flow. So you're limited by your application to use a single flow. This does not apply if you're in the same cluster placement group. And again, if for an HPC workload, that will work just fine. You could place those in the cluster placement group. My recommendation, though, would be to use multiple flows just because that gives you way better scalability and resiliency as well when using the network. Another limitation, so and again, this is going with what you should know when testing those performances, is that you do have other limits associated with a single instance. The first one is that we discussed is the inbound and the outbound bandwidth, which is defined by the instance type, but also you have a packet per second limit. Processing packets has a cost, and while this limit is extremely high, especially on the newer instance types, you still might get to the point where you will be limited on the number of packets per second you can send. This is normally a bit more of an issue for real-time applications or applications that are very chatty, highly transactional. You will know if you have this level of application that this might be one of the considerations you need to have. The third one is around connection tracking. This happens with security groups because they need to keep, since security groups are stateful, it needs to keep track of all the connections that are being made. And again, there's a limited amount of capability. It's a very high number, but it's still something to keep in mind. It basically, security group need to keep in mind, to keep in memory how many connections are being opened and what's the state of those connections. I've added a few links with a bit more information on that. And then you have last limit is the packet per second to link local services, and link local services are services such as the VPC DNS or the metadata service that's available to every instance. Again, you will likely never hit this limit if building properly, but it is something to keep in consideration. So customer will hit those limits and will try to figure out where the problem might be. So in order to empower our customers to know more about this and what are those limitations, we starting from the NI drivers from version 2.210 and above, those are exposed as counters for the network interface. So anytime there is a drop because we reach one of those limits, this will be available in the driver itself. There is a link for that regarding this in the chat on how to enable this. And you can also export this data as CloudWatch graphs as well. And I'll add a link as well on how you can do that. It's not available in CloudWatch by default. You will have to have every instance exported, similarly to how you exported the disk utilization, for example. But it is something that needs to be done on the from the instance itself. And this is something, again, you will know if you're hitting this limit, then you need to consider how maybe you need more instances, maybe you need bigger instances, maybe what you selected is not the right level for your workload and will allow you to better make your decisions when building on this. We have a question from RayDB222, question on monitoring instance bandwidth. Do you recommend to configure EC2 to send metric data to CloudWatch in 1 minute or 5-minute periods? Is one better? Milan, do you want to take this?
Absolutely. Ray, thank you very much for the question. And it's a really good one. So it depends. As Francesco was saying, it really depends on whether you're trying to monitor. So when it comes to monitoring the network bandwidth for your EC2 instance, those come out outside of the box as part of the standard set of CloudWatch metrics. You can enable enhanced monitoring, which will increase the interval to 1 minute. So that way you can have more granularity. However, when we talk about the allowances here in the context of this question, it really depends how your application is sensitive. Like, do you want to know about the event that has happened 5 minutes ago or 1 minute ago, and how do you want to approach and scale? Given that you might be hitting, for example, a connections per second limit, right? So it's very very important to understand exactly what would you like to do. However, you can even go further than down a minute. Like if it's a very business critical system and you need to know that you have to react faster, you can configure the metrics exporter on your instance to send custom metrics at a lower period, lower time frame. Obviously, this is going to come with some other pricing considerations that you have to keep in mind. But in the end, ultimately, it really depends. And these metrics are usually good to start with, let's say with a 5 minute interval, and observe them over a period of time. And then if you start getting more consistent hits in any of these, you might want to reconsider looking into a minute interval, or even something that's on a lower level interval than a minute, depending on, again, what is the perceived impact to your application.
Perfect. So, and again, thank you very much for the question. And you will notice that there is a lot of it depends. Again, that's the theme of these specific episode, and it really will depend on what you're trying to achieve. But if you do know what are your limitations, what is that your application is limited with, for example, bandwidth, you might decide to scale on that, and 1 minute metrics might be the optimal choice. If you are bound by CPU and you're scaling off CPU, once you selected the right instance size, then maybe it matters less, and you might not want to use the detailed monitoring for the bandwidth, for example. So going forward, before I get back to Milan, I wanted to talk a bit about the packet per second and the maximum transmissions unit. So we talked about this before, but we do recommend to use jumbo frames whenever possible. This is not something that's generally applicable to all workloads. Again, if you have a very high transactional with a very small amount of data being exchanged, MTU is not going to do much for you, because you will not be able to fill an entire packet unless you are trying to aggregate data, but that will increase the latency. The reason for this is because each packet has a processing overhead for all the systems that are traversing it, from AWS and the ENI, the operating system, and your application itself. So limiting the number of packets that are traversing the network will allow you to get better performances for all intent and purposes. Unfortunately, as we said, 1500 is the facto standards over the internet. So anytime you're talking with clients that are exposed over the internet, you will not be able to do much more than that. But if you are doing a heavy query on your database, or anything really that you could benefit from inside the AWS network, using jumbo frames, which is, by the way, enabled by default in the latest Amazon Linux 2 instances, will allow you to be more efficient in terms of package processing. To a point, Milan, I know that you're an expert on this and you've dealt with this with a lot of customers. I wanted to talk a bit about the performance consideration we need to make when using the Elastic Network Adapter.
Thanks, Francesco. So I just want to give a little bit more broader. So this relates to any network adapter, but obviously we're going to be talking from the ENA perspective, given that there are certain ways how to troubleshoot ENA. So whenever we talk about the driver performance in the Linux operating system, there are a couple of very important key points to keep in mind, which is how does your overall system behave? Do we have a high, let's say, CPU utilization? Because ultimately that CPU has to be used to process a network packet. So high utilization of CPU can indicate, can lead to certain behaviors in the networking driver that will degrade your networking performance. So always have to be considerate about like the potential CPU starvation because of the interrupt request queues and the way the packets are processed in Linux. One thing as well to keep in mind is receive drops, and they're titled here as an RX drops. And it's one of those things when you look at your instance, and all of a sudden, let's say that you're using a Linux operating system, and you do an if config, and you see that like the packets are being dropped, like the inbound packets are being dropped, but you don't see them anywhere in like your TCP dump or up higher up the stack. So there are certain queues which are the receive descriptors, and what they do is literally they represent a hardware buffer towards certain descriptors that are, the packets that are in flight, where the driver can read them from the memory of the NIC itself. And then, if you're falling behind in reading those available descriptors, the system has to draw packets, because simply, there's a finite amount of memory available and space available in the descriptors that you can use. So there are ways to work around it and tune this. For ENA specifically, you can set these up to 16K descriptors. It starts on the default on 1K. And we have, like, over, as Francesco said, over the period of years, we have worked with many customers in different industries. And this has been one of the most common things that we looked into. Hey, the customer would have a very high CPU utilization that will lead into packet drops, and then what are the potential things that we can change and tune to maximize the available bandwidth. But not only the bandwidth, doing some of these performance tunings for the driver itself, you can even further reduce the latency. Obviously, playing too much with these knobs, can have detrimental effect for your environment. So this is why we always say, test it for your environment. And when we interact with our customers, we're always very closely aligned in understanding exactly what the environment looks like, how can we test it, what are the best times to test it. With anything else in Linux operating system, one of the common things I've seen across the board is you get this very large instance types which have multiples of hundreds of gigabytes of memory, if not terabytes of memory, and then certain allocations for the kernel itself, which is like what is the available memory for the kernel, are left by the operating system defaults. And these are usually are like very small. There are some things that get tuned automatically, but like given the DNA is a kernel driver, therefore it benefits from having more available memory for its pages. So this is one of the tunables that we also recommend to our customers to look, given that what is the system state overall and memory pressure. And over the period of years, we had a lot of these. So we work with our ENA team to compile a document, which is very in-depth document about performance testing and tuning for ENA. And it touches anything from your CPU starvation, your interrupt remapping, how to ensure that you use the maximum affinity for your cores, and how to drive the maximum performance, for instance. So I highly recommend checking it out, because probably there will be another talk here just to talk about this. So when we talk about performance testing, one of the questions we get from our customers is how. Okay, you told us to test it ourselves, but how should we do that? And as Francesco has mentioned, what we usually go and say is, test it with your application and your environment, and or something that mimics as close as possible to your application and your environment. Because load testing gives you very informative and useful and important insight, and that's what are the breaking points, when are the pagers going to go off, when are your customers going to have a negative experience. So this is why you always you want to do some form of load testing, just to know where your system bodes, and what is the maximum that can go before your customers are starting to get some negative effects. That can be just your sample load testing, like what is the maximum number of transactions that we can do, like which is like the racetrack numbers, like which is the maximum that our system can do before everything falls apart and nobody's happy anymore. But also there are very useful things when we talk about benchmarks, and that's goes back to your overall environment and our architectural discussion from earlier. you know, you want to know, what is the maximum bandwidth, for example, for a flow that's intra VPC or towards the internet, or that traverses back to your on-premise data center using VPN. What is the maximum bandwidth, latency, jitter, throughput, and packets per second. So those are like your benchmark overall environmental testings. They are really good and really useful. Most of the times, are something that are not a concern for majority of the customers. And it's the first one, which is the application and the configuration of the environment, which is what makes it very important to test. And some of the testing tips, as Francesco mentioned earlier, there are inherited limitations on a single flow, which is 5 gigabits per second for a given five tuple. So when we talk to our customers, we always say, we need to use multiple flows in order to saturate the bandwidth maximum to the maximum, because single flow, we know that it's going to be limited to 5 gigabits per second. It's going to be 10 gigabits per second for a placement group, but that's it. We know those things, and that's why we say, hey, let's always try with multiple flows. It's also important to use UDP. And we've talked a lot about TCP here, but UDP has some very niche positioning when it comes to performance testing, simply because it lacks a lot of controls which TCP has. So, if you want to say what is the maximum number of packets that can drive on this instance, well, you can use UDP using iperf and the command that's on the screen, but adding the lowercase p, sorry, lowercase u, and then the lowercase p were a port number. So lowercase u represents the UDP as a traffic. So that way the iPerf is going to start sending UDP traffic. Obviously, the remote end has to be configured to receive UDP traffic, but this will give you a test of there's no congestion control algorithms, there is no smart recovery or anything like that. This is like bare bones. How many packets can I put down the wire, and how many packets do I receive on the other end? And this is very fine for single to host scenarios, but a lot of our customers have environments which are fairly more complex, and running these commands while possible manually, it takes time to provision capacity. So, another team within AWS has written a really amazing blog post about distributed testing tools and how can you use the solution that was built on top of AWS using Fargate to do a distributed load testing on AWS from a very nice from a very nice user interface. You get to choose what you want to test, and you get all the results out. And Francesco has already shared we have a very specific link about network throughput benchmark for EC2 Linux instances. So I highly recommend checking that one out because it gives you a lot of in-depth about what can be done. And I've seen that we've mentioned FIS, which is fault injection simulator. It's a great service that I think everybody should start slowly incorporating in their load testing, because load testing is great, as it gives us what is the maximum performance that we can get. But there's always this question of like, what happens if something breaks? And this is where fault injection simulator is a really good tool that can enable you to simulate, for example, network latency. So it uses custom SSM documents that you can run as part of your experiment to introduce the latency in your environment, to go up to whatever the number you want it to be, and see how your environment behaves. But also you can do packet drops based on a certain destination and port, like sampling not every single packet, but like a percentage of the packet. So like it's a very, very important and very powerful tool to sorry powerful service, but a tool in your performance testing toolbox. And sorry, go on,
Perfect.
Francesco.
Thank you. No, sorry. I wanted to add a couple of notes here. We have an episode on fault injection simulator that we did on AWS Supports You with our colleagues. I posted the link in the chat, so go watch it. It was pretty awesome. So if you want to learn a bit more about the service, just wanted to now touch a bit on an example that, while not interactive, we prepare to show you once you have taken all those consideration, what are the things that you can tune so that you can achieve a better performance. So with all things equal and all things considered, is that you have one test server, one test client instance that are hosting a high transaction rate HTTP service. Basically, this application is meant to serve a lot of requests coming from a lot of different clients in as fast as possible. If we do assume 80 milliseconds of round trip time using HTTP and not HTTPS, you should always use HTTPS. But for the intended purposes of this test, this is to remove the element of encryption, which consumes CPU cycles and might slow things down a bit. Taking consideration of 1500 MTU because we're considering traffic over from the internet. We're starting Apache Benchmark. Again, this is a tool from the Apache Foundation that allows you to simulate HTTP requests and sending 200,000 requests for a 10 kilobyte object served on the server with a concurrency of 200. What we want to do with these, since we cannot really change network, we don't want to change the distance type, is to tune a few TCP parameters and see what are the results of tuning those TCP parameters in terms of the efficiency. The reason why we're tuning, as Milan was saying, is that out of the box, all instances and operating system are configured to do a good enough job for all the purposes. So there is no specific tuning to one specific workload or not. But now that we tested our workload, we know what our workload workload is, we can try to tune things so that it can work a bit better in our favor, and we can get better performance from the get-go. As we mentioned before, one of the way you can get better throughput is by sending more packets. And the TCP protocol uses the concept of congestion windows to determine how many packets to send in one go. And this is something that you can influence by it's a setting that goes per route in the operating system. And you can change this initial congestion window to tell to send more packets. The reason why this is not as high as possible is because if you send too many packets and the network quality is not up to the task, then it will end up with packets being dropped and the congestion window shrinking more aggressively that it can grow. And again, this is a part of the different congestion algorithm that TCP uses to determine how much at once it can send before things start getting a bit too busy and we start observing packet drop. Same thing on the remote side, we can tune the receive window so that it can hold more packets. Maybe you have the disk that might be a bit slow at times, so you cannot write. You want a bigger window so that you have a bit of a bigger buffer in memory before those packets are processed by your application. And as well, changing the congestion algorithm. We probably will need to do an in-depth session around congestion algorithms since there's a few and there's different reasons why those algorithms behave differently. The other thing that you can change is the retransmission timers. So basically how long it takes before a packet is retransmitted if you don't receive an acknowledge. This is something that you can tune, but it is a very dangerous parameter to tune. This is because you can easily end up in a retransmission storm if you set it to be lower than your regular round trip time, because it will trigger retransmission simply because the packet has not yet arrived. The packet is going to arrive, but maybe it's 100 milliseconds away. And if you set this to be lower than 50 milliseconds, then obviously the of 100 milliseconds, obviously you will get a retransmission on top of retransmission on top of retransmission. But again, those are the four main parameters that normally you can start looking at. You can start moving the parameters, tuning them a bit, and then see what the effects are when testing it. Again, always test before setting anything into production and be ready to observe what the behaviors are. With that said, if we go on and look into the results, so if we do start with an initial congestion window, so 3 packets, we can achieve from the get-go 12 megabit per second with a P50 latency of 321 milliseconds, all the way to improving it with a congestion window of 16 packets to a 79% increase, achieving a bandwidth of 22 megabit per second. And this is simply because we are able to send more and complete our job quicker. Eventually, with a big enough job, we will be able to achieve the same level of bandwidth if that job were to run indefinitely, because the congestion window will grow. But for if the workload is bursty or it's getting in a short amount of time, obviously you can see how these can become a bit more efficient. Okay, with that said, just last couple of comments on that I wanted to make. We're almost at time, so I wanted to just give a recap of what we talked about today. So we looked at how customer can rely on the underlying network for all their different needs. So they use the network for different applications, and all the consideration that you need to make is, about the network and the applications and the resources that you're using, so you can build an efficient application on AWS and be successful with your customers. How you can use different EC2 components to help with testing and make the right decision, and a few tips on how to optimize your resources for performance. I want to thank Milan for joining us today, and all of you for joining us today. And if there are any questions that were not answered today, you can post your question on repos.aws, where one of our experts can provide you with an answer. And your question could actually become a topic on one of the future shows. But if you have any feedback for us, please check the chat box for a link to the survey, and you can email us at AWS Supports You at amazon.com. Thank you for joining us today at AWS Supports You, and happy cloud computing.